fact, this is one of your homework problem, and we sort of looked into it on Wednesday. But consider if I have two infinite slabs, right? It's infinite, and then you separate it by distance s, right? And then you put the, let me get my sign right, you put the minus sigma here, plus sigma here, okay? And for the purpose of a lot of discussion, I'm going to find sigma to be equal to the charge divided by the area, right? Suppose you assume that this slab is not completely, doesn't extend all the way to infinity, but has some area A, where the square root of A is much larger than S, right? Square root of A is much larger than S. By the way, right, when you do your exam, the easiest thing to do is check your unit, check your dimension, right? If you're dividing temperature, right, temperature, say one of the problem, but temperature divided by L, right? You immediately know something is wrong. Because this is the unit of energy, but the heat is the unit of energy. And suddenly you have a unit of length, right? So something must be off. Right? Anyway, so the square root of A is much larger than S. Let's find the field everywhere, right? So we know from our study of infinite slab, if you assume this is much larger, this is true, right? Then just from the plus sigma slab, you have electric field going is equal to sigma over 2 epsilon naught here, and sigma over bring this fast because we did this discussion on Wednesday, right? And then coming from the negative slab, right? This extends all the way to infinity, by the way, right? This is clear. For an infinite slab, it's constant regardless of the distance from the slab. Same thing for the minus sigma slab here. The field, by the way, is inward because of minus. It's minus sign, right? Okay. And it's given by sigma over 2 epsilon naught here, and sigma over 2 epsilon naught. Okay. And so the field, let's divide this into this region in 1, 2, and 3, just like on Wednesday, right? In region 1, the electric field cancel. The electric field coming from minus sigma exactly cancel the electric field from plus sigma, right? That's 0 here. By symmetry, the electric field, total, by the way, is also 0. Okay? And the electric field in region 2 is all pointing towards left, right? It's given by the sum of these two, sigma over 2 epsilon naught plus sigma over 2 epsilon naught. The field here is sigma over epsilon naught. Okay? And make sure that you check, if you remember, the boundary condition. This is always true for electrostatic. The boundary condition E3 minus E1 in the normal direction has to be equal to the surface charge density divided by epsilon naught. In this case, it's true 0 here, sigma over epsilon naught, and then 0 here. Right? So this is true. Okay? Now, I want to find the potential everywhere. Right? And the potential is given by the integral of minus E, right? And in this case here, I am going to take my reference to be, you have to choose your reference nicely so that, the problem is simplified. I'm going to choose my reference so that my origin, the coordinate is at the left slab here. Okay, this is what C, X and Y, and I'm going to divide potential at R minus potential at 0. Okay? And I'm going to divide potential at 0 to equal to 0 to be equal to minus E, yes, from 0 to C. Right? This is the potential only depend on C. Okay, and then you calculate this for this electric field. Okay, then you will get the potential as a function of C. If you do your math right, it's going to be equal to sigma C over epsilon naught. Okay, so the potential looks like this as a function of C. This is 0. This is S. Right? Potential is 0 everywhere because there's no electric field here. Okay, and then in these two regions, they become linear with a slope given by sigma over epsilon naught. Right? And outside is again constant, right? Because the electric field is 0. Okay? And you can show this is true by just doing this integral. Right? It's a very simple integral to do. Okay? Also, a lot of people make this kind of mistake, right? The integral of 1 over x from x1 to x2. Right? And they write it as a log of x2 minus x1. Right? It's not true. It's equal to the log of x2 minus log of x1. Just an aside. Okay, and what is the potential at S? Right? It is the potential is the potential at 0 is 0, and the potential at S is given by sigma S over epsilon naught. Okay, and let me substitute Q over A for sigma. Then I would get the Q S over A epsilon naught. Okay, and if I look at the potential difference, delta V, the delta V is this V at S minus V naught is given by Q S over epsilon naught. This is the potential difference between these two slabs. Okay, and the equipotential surfaces looks like this. Right? Okay, and the potential increases as you go from the left slab to the right slab. Okay, and the electric field always points from high potential to low potential. So the electric field goes this way. Okay, simple enough, right? Okay. Another problem that you could do, and I'm not going to do it in detail, is when you have concentric. One radius RA, another one radius RB. Okay, if I put plus Q uniform on the shell, okay, and minus Q on the shell RA, and minus Q uniform on shell RB, right? Where sigma A is Q over 4 pi, the area of the shell, 4 pi RA squared, okay? And the flux density at B is given by minus Q, 4 pi RA squared, right? Okay, you can do similar calculation like that. And it's actually very easy to do. We know that the electric field, let's call this region 1, region 2, region 3. The electric field in region 1 is 0, right? The electric field at region 3, by Gauss law. This thing has a spherical symmetry, right? So inside here, the Q equals 0, right? There's no charge, electric field is 0. Outside, in region 3, right? What is the electric field here? Again, it's 0 because they in a situation where you have a spherical symmetry, then the electric field at a point outside is equal to electric field coming from all these charges as though they are actually concentrated at the center, right? So plus Q minus Q is 0, so you can treat electric field as 0. Okay? And you can easily show that in region 2, the electric field is given by Q only from the inner shell, right? The outer shell is still giving 0 electric field. On the inner shell, you get 4 pi, so now 1 over R squared, right? This you know, right? Okay? And let's calculate the potential. Potential again is given at R, or E, R, okay, or ETS, just to use a different variable. Okay, and I'm going to take, in this case here, the reference to be at how did I do it? I think it's so I'm going to take my reference point to be RP, right? So V at R minus V at RP, which is the outer shell, is equal to minus integral from RP to RA E yes. Okay, and we set the potential at RP to 0. Okay. And when you do that, when you actually substitute this electric field into this integral, if you do it correctly, making sure that you don't make a sign mistake, right? At the end of the day, you just look at the result and make sure that it makes sense. Sign mistake usually is easy to catch. You find that VR is going to be equal to Q over 4 pi epsilon naught. 1 over R minus 1 over R. Okay. So if you look at the potential, if I draw it, the function of R is RP, RA, right? It's going to be 0. Okay. That's 0, and then it's going to be 1 over R like that. Portion of 1 over R. Okay. And then it should be constant. Okay. It's constant, and it's constant here because the electric field is 0. Okay. And the potential at RA is given by Q over 4 pi epsilon naught. 1 over RA minus 1 over RB. Right? And if I define a potential difference to be the potential difference between these two shells, right? VRA minus VRB, right? This is just that difference. Just equal to that, right? Because VR 0 is 0. So this is Q over 4 pi epsilon naught, 1 over RA minus 1 over RA. Okay, and this is positive, right? Because RB is greater than RA. Okay?
Is the potential 0 outside the sphere?
Inside the sphere for, no, it's not 0, it's constant. Right?
It's constant the close to the sphere.
It's constant.
Sorry, outside the sphere.
Yeah, outside the sphere is 0. And this is, you define, and you can define whatever you want, right? Because as you know, just like in energy, you can add a constant to it, right? So I can just scale this, right? I can scale it, oops, it's kind of a scale. Right? I can scale things up and down, and it doesn't change the answer, right? You can always add constant to your potential, right? And I just choose to define it. You can define it however you want. In the end, the physics doesn't change, right? I choose to define it that the potential is 0 at RP, right, for convenience. I can choose it to be 0 over here, right? If I choose it to be 0 over here, then the graph looks like this. Like that. Okay? And at the end of the day, it doesn't really matter. Okay? So,
So why is the potential constant for inside the sphere when E is 0?
Because what happened is, remember the definition of a potential, right? It's a line integral of electric field times ds.
Yeah.
So once I reach that point, right, in this region, the electric field is 0, right?
Yeah.
if I want to continue on with the line integral, right, then the line the segment of the line integral from RA to R inside RA is identically zero because there is no electric field. Right? So the potential is constant. Because I just take this integral, I take it from infinity, right? Somewhere in infinity.
Oh.
I take it over here, everything is zero, right?
Yeah.
The line integral is zero. When I take it into region 2, then the potential start to increase because there is an electric field, and it should increase as 1 over r, right? Because it sees an electric field that goes as 1 over r squared,
Yeah.
right? And then when it goes into region 1, suddenly it sees a zero electric field again, right? So there is no addition to the potential anymore.
Okay, and there's
Potential
nothing to
becomes
change it either to make it lower or
Yes,
higher.
yes,
Okay,
right. So it becomes constant.
yeah.
Right?
that makes
So
sense.
if you remember, electric field is the gradient of the potential, right? So in this case, there is no gradient. The potential is flat, so the electric field is zero, right? And here, because of the 1 over r, there is a gradient.
Okay, so you can't just plug it into this one then and say 0, the interval 0,
You can,
0.
you can, no, you can. Here, phi at infinity is equal to phi at RT is equal to 0. You just have to do the integral correctly, and it's not that hard.
Okay.
I just don't want to
No, okay.
make a sign mistake in front of you guys.
I mean, and it's just sort of like, if E is equal to the sort of the full derivative of V, then for E to be 0, V had to be a constant.
Yes,
Oh,
derivative
because
of
V's that
constant.
one. Okay.
Correct.
Okay.
Okay. So that's that.
Oh, wait, so this E here is like the vectored E, whereas this one's just like the...
Say it again.
Because I'm confused, because I would have thought of this problem straight up like, oh, E is 0, so I would have just plugged in 0 and then gotten V of R is 0, but then that's
No,
not the case
right,
here.
It's not the case.
Yeah.
No, potential is the gradient of electric field, and you can always add a constant to a potential.
Okay,
Right?
so you have to
But
think of
you
it...
just have to be consistent for a particular problem, right?
Mhm.
Because potential always, you can have discontinuity in the electric field, you cannot have discontinuity in the potential. That's just a solution of a Laplace equation. Right? So it has to be continuous. So if your potential is like that, it has to follow continuously. And at the discontinuity at RA, you have a shell, right? And it still has to be continuous. There can be a kink because they have a different slope inside and outside, right? Because they have different electric field.
Mhm.
But the potential itself has to be continuous.
Yeah, that makes sense. Like,
Okay. So with this background in mind, I want to compare something. Let's erase that. Let's move on to discuss what the best we can. But before we do that, let me make a few remarks about the class equation. Often in a study like this, right, as I said on Wednesday, you don't have control where to put the charges, right? Because it's very difficult to move charges. Most things, they are quite balanced with plus and minuses, right? That's why it's so difficult to bend stable, right? Bend metal. It's because when you do that, you're trying to change the distribution of the plus charges and the minus charges, and that's difficult to do. You almost have no control. The easiest control that you have is potential. In the lab, you can control the potential. Okay? That's the reason we actually want, to go through the trouble in H7B and which you do in 7B, say, right, to look at the divergence of electric field is equal to epsilon naught, and then this leads to a Poissonian equation. The Laplacian of the voltage is equal to minus rho over epsilon naught. Okay? In particular, in a region of free space, right? This is true. Okay? So you can plug this formula. You can just plug this formula, the divergence of the Laplacian, into any of these equations, right? For both the the potential for the, I erase it, the potential for the infinite slab in parallel plates, right? Plug the expression for the voltage or the potential into this equation, or look at the divergence of the electric field, right? You'll find that is equal to 0. Inside, right? Meaning in this case it's inside the parallel plates, not on the slab itself, right? For now, I don't care about the slab. I define the slab to have certain charges, right? But if I look at the region inside, it will satisfy this equation, right? We can usually try to do it. Same thing here. This region inside, everywhere here, or in fact everywhere, right? Except for on the shell, this is always true. Now, when you do an experiment, and this is with conductors, by the way, but for now let's not consider that too deep. What you control is the voltage difference, right? So it's, instead of having plus Q minus Q here, what you have is V at 0 to be equal to 0, and V at S to be equal to sigma S over epsilon naught. Okay, or some sigma, or something. And the question is that find the potential everywhere, okay, with the following boundary condition. This is the boundary condition. This is for the infinite slab. This is the boundary condition, right? For the concentrics here, right? The boundary condition is V at RB is equal to 0, and V at RA to be some number V naught, which is what you calculated to be Q over 4 pi epsilon naught, 1 over RA minus 1 over RB, right? But for the purpose of this discussion, it's just a constant. Given a constant inside and 0 outside, right? Do I have solutions? Do I have a solution for potential F? Okay. And to solve for that, you have to solve for the Laplacian, right? You have to solve basically, you have to solve for this equation equals 0, right? So this is math 54, 53, right? Differential equation with boundary condition. For this problem, the boundary condition is this. For that problem, the boundary condition is this. And this is simple enough geometry that you can do. In a lot of cases, you can't. Right? You can spend 1 or 2 semesters at DNM, which is basically solving that kind of equation. But there is a beautiful simple theorem, it's called the uniqueness theorem, that shows if you can find one solution, right, this is in Purcell, right, it's a consequence of the Laplacian. Right? If you can find a solution, that satisfies the Laplacian and then boundary condition, then it must be unique. Okay. And if there is no recreate, I'm going to prove that. But for now, just take it as true, or in Purcell, right? There's a good proof there. But yeah, take it for granted for now that if there is a solution, it must be unique. And you did find a solution, right? You did find a solution not by solving the Laplace equation. Right? In this case, we just solve it to that brute force by looking at electric field. Right? From the electric field, we calculate the voltage, the potential, right? And we found a solution. Right? And therefore, that solution must be unique. That's the only solution possible. Okay. For infinite slab, just call for infinite slab. E is 0 times E smaller than 1 times C. And then for the concentric sphere, I'm just rewriting this again and again. Q over, I can just specify Q naught, 1 over R minus 1 over R. Right? And then of course, I make a dimensional mistake here, right? I already said that don't get your unit wrong, but I'm doing the unit wrong here, so you have to, this thing has to be all normalized by some RA or something. So just to get the unit right. But the dependence is 1 over R. Okay? So this is the solution. And if you look at it, you might ask, well, I thought the idea is you can add constants. Right? So where is the uniqueness?
In the derivative of the constant being 0?
No. Because,
I think you mean since the boundary conditions is effectively.
yes. The boundary condition set what that constant is. Right? Because of the boundary condition, right, there's no choice. You cannot move it up and down. Because I have to make sure that the potential is 0 here and it's sigma s over, or it's V naught here, right? Okay? And it's V naught here and it's 0 here. Right? That pretty much set what that constant has to be. Right? The functional dependence is still the same. It's still linear in the case of a slab. It's still 1 over R in the case of the concentric shell. Okay? So now you have everything at your disposal to actually understand vectors. I was talking to Trevor yesterday or 2 days ago, because a lot of people might confuse conductors. In this case, we're considering a static configuration, right? Nothing moves, right? So there is no current, right? And a lot of you probably learn this from high school or junior high, where you play around with electronics, right? Hanging with wires that act as a conductor and the charge is moving. Right? That's a steady state solution that we will look into in the next chapter. But for now, we're looking at a static configuration, right? For our conductors. It's a perfect conductor, meaning that anytime you establish electric field inside or anywhere on the surface of the conductor, right, charges will move. Will immediately move to cancel the electric field. Right? So E is 0 everywhere. Rho of E is constant everywhere. Inside and on surface. Okay. And that's rho is 0 inside. Okay. But you can have surface charge, right? And because of the surface charge, that's surface. Okay. Then the electric field normal, right? Going to be given by sigma over epsilon naught. Right? This is from Gauss law, right? The first thing that I wrote earlier. Everywhere here, there is always if there is a field, it will be normal, right? And it's 0 in here, right? And electric field parallel to the surface. This is normal to the surface. This parallel to the surface has to be equal to 0. This we also established on the On the conductor, the field always going normal at the surface. Okay? So, and then we look at I did prove that the inside the cavity is 0. If I have cavity, right, E inside. Okay, so we can prove that. I'm not going to repeat it because it's a bit, I like that better, it's very physical. Make sure that you understand it. I'm not going to get into the discussion. But you can also use Laplace equation to prove it, right? Because the potential at surface, at inner surface, is constant. For a conductor is constant, right? Suppose it's V naught. Okay. This is your boundary condition. And inside, in the free space region, it has to satisfy the Laplacian of phi. Has to be equal to 0. Right? Okay? But one possible solution is just phi inside is just equal to V naught. Right? If V inside is just equal to V naught, right? The Laplacian is 0. The Laplacian of a constant is 0. Right? And they satisfy the boundary condition. Because at the boundary, the potential is also V naught. Right? So this is a possible solution. But by uniqueness theorem, it's also unique. There is no other solution. Right? It's just how powerful it is. Right? So this is the only solution possible. Therefore, the electric field is the gradient of B, right? Is 0. B is 0 inside. Is that clear? These are some general statements that you can make without even solving anything in particular, right? Just looking at the general condition of the differential equation. So let's look at a few examples of that.
Would that imply that every solution to del squared equals 0 is always constant?
No, not necessarily. Like this is a special case, right? Meaning that in general, it's the most difficult to find, right? The whole branch of mathematical physics is solving that with the right kind of boundary condition. We have a very simple boundary condition here. Right? This, I don't know about getting to that because, in just time. If I have conductors F, let's say, right, in some kind of linear configuration, finitely distributed, right? So I can set down 1, 2, 3, 4, and at infinity, right? The other boundaries at infinity. Say, for example, the concentric circle, I can also do the same thing. I can set this one at infinity, and I just have one shell. This shell can be infinity. Right, just another particular example. But in this case here, I have to solve equal 0 inside in the intermediate region here, right? With the boundary condition given by this arrow. Right? And in general, the solution is complicated. Right? And you cannot find one. But if you can find one for whatever way, it has to be unique. By uniqueness theorem. By the way, it's not general enough. That statement is not general enough for the information. It's sometimes, you don't have to define the potential only, but it's technicality. It's also about if you can define sigma everywhere. Right? So sigma is just E normal, right? So it's equal to Vn, right? So if you define sigma everywhere on the surface, also if you find the solution, it's unique. Okay, but we're not going to go into that. Okay, so let's look at a few examples of conductors. this spherical shell, right, of perfect conductor, RARP, we just do this one only. If I put plus Q in the middle, what happens? By the way, while you think about it, if I have a cavity again, any cavity, right? And suddenly I leave plus Q outside, okay? It will polarize the conductor, right? Charges are free to move, in this case, minus signs will move here, right? Plus signs will move over here maybe, right? But it's done in such a way that, when this is a physical problem, right? It must have a physical solution, that the electric field is zero inside. Right? Even though you have plus Q, minus Q, whatever in here, right? You have perfect screen. For perfect conductor, you have perfect screen. And this is really nice for a night fair, right? This is called the Faraday cage. To do that kind of execution all the time. But how about in this case here? If I put the plus Q inside,
How about negatives go around the middle?
and this whole thing has a concentric spherical symmetric condition. Sorry? That's the question, right? So let's analyze it a little bit at a time, one step at a time.
So wouldn't like the inside surface become negative and the
Yeah.
outside surface become positive?
Yes, but to be specific. E inside E in the mid of the conductor, right, has to be equal to zero. Right? You know that from the definition of a conductor. Right? Okay. So by Gauss law, if I make a mathematical sphere around here, right? Okay, as a Gauss law, EA has to be equal to 0, right? Because the electric field is identical to 0 for S inside the conductor, right?
What's S?
S is just a mathematical Gaussian surface.
Wait, is this a single conductor with like a cavity in it?
Yeah. This is a.
It's not two concentric shells that are
No,
not
this
space
is-
in between them?
This is a cavity. Yeah.
Oh.
I'm sorry, I didn't write it
Oh,
well. Right? I'm in a hurry. It's always better to be in a hurry. If I have a cavity, so I have a sphere, right? A sphere of radius RV,
Yeah.
right? And I carve out the inner cavity of RA, right?
Yeah, it's negative.
Okay? And I put plus Q in the middle, right? What happened, right? So, we know that the electric field inside the conductor is 0. Therefore, the flux for the Gauss law has to be equal to 0 for a surface that's in here, right? Therefore, since Gauss law says this has to be equal to 1 over epsilon naught Q enclosed, right? Q enclosed has to be equal to 0, right? Therefore, what happened, right? The conductor is infinitely polarizable for this ideal case, right? Then what you have is your minus charges which distribute itself uniformly on the inner surface, right? And the total is minus Q. Minus Q is uniform on the inner surface of RA, right? That would guarantee that Q enclosed is 0, right? And then because the conductor is neutral, right? The conductor is neutral, therefore you must have plus Q on the outside. Okay. What is the distribution of plus Q in this case? It's also uniform, right? Just because of spherical symmetry, right? Okay? So how about if, let me continue on next time. I have 3 more examples like that. But this is your midterm, If some of you came late, it doesn't mean anything, right? It doesn't mean anything.
That.
More than 50% of the people have scored between 65 and 75. Highest score, 88. Average is 67 or 68, I don't remember. Right? And if you're not happy with the midterm, regrade is immediately after. If you're not happy in general with the course, whether you got 88 or whether you got 0, right? You can be unhappy even if you have 88. That's often very happy.